Yeah, I think it's 12 o'clock. Is it okay for me to start? Yeah, so hello everybody. My name is Astrid Maaß. I'm from the Fraunhofer Institute in St. Augustine for Scientific Computing and Algorithms. So although I'm here in the battery section of this session of this morning, I will be talking mostly about data. So the title is Holistic Battery Knowledge, the Foundation for the Digital Battery Passport and Data-Driven Process Optimization. This is very fancy for a given reason. The European Parliament and Commission have ruled that in 2 years' time, almost accurately, every battery of a certain type in Europe has to have a digital battery passport that is an electronic record of data relating to a battery. So this concerns batteries for light means of transport, for energy storage systems above 2 kilowatt hours, and electric vehicles. And all those will have to carry a QR code. And if you check the link, the data detailing information of this specific battery have to be provided via a portal. So the purpose for this regulation is that the union wants to transform the union into a fair and prosperous society. So they want to achieve resource efficiency and competitiveness. They want to cut down the greenhouse gas emissions, and the procurement of the batteries should be responsible. So the current state of affairs is that in the lithium-ion battery life cycle, well, it's not a life cycle currently, it's a linear flow of materials. So we're starting from the raw materials sourced currently mainly from Australia, China, and South America. And so it gets then refined to high quality grade chemicals before being able to put into cells. And those cells get connected to higher order assemblies to form a pack that finally ends up in an electric vehicle or in a storage cabinet or on an electric vessel, for example. So only then it enters into the actual use. So far, the entire all those steps and processes are the ones that require investment in terms of resources and energy and material. Only then they become useful during their life in a car or a certain application, as we've seen. And at one point, so many thanks to Daniel before, who motivated very much of what I have to say now. So irregardless of how nice you are driving your car, at some point in time, the battery's capacity will have faded below a certain threshold, which makes it no longer economic to drive the car with those batteries, and they get retired. And mostly so far, they end up then finally deposited on a landfill. The European regulation tries to achieve that this currently very black picture turns into something more sustainable. And obviously, the use of renewable energies for the charging the batteries is one step in that direction. But much more important is to turn the material flow into a cycle. And that implies that cells are collected after their life. They have to be sorted, so they carry valuable materials, but they come in varieties. So there were several questions about what type of chemistry you're using with. And you have to demix those collections by types of chemistry, for example. You would then have to open and dismantle batteries, which can be a risky undertaking if you don't know the state of your battery. And then, of course, you have to split up the cells themselves and recover the material. But this second circle, so the undoing of the supply chain, the reverse supply chain, is really much more efficient than sourcing the raw material from mineral deposits or from brines. Combining first life application possibly with a second life application would even more, the batteries would last longer. So for transportation, where high energy densities are crucial, they become useless after maybe a capacity fade loss of 10 to 50%. But that still leaves us with more than 80% of capacity for different applications. So the trend goes to put them into charging boxes, for example, where they can take up slowly energy from solar system and deliver it to the car then. So it's the transition from first life to second is intended to be the one from car to the cabinet. Recycling would perhaps not have to be would not have to cover the full cycle, but could have some shortcuts even. So if you have collected and sorted through your batteries, if you can reuse parts, then and refurbish batteries, then this would be even more economic than undergoing the full recycling stage. So currently, the battery packs, we have seen it, individual cells are combined and welded for better contact into larger modules. And one bad cell in such a system, a component, requires the whole component to be replaced. So one bad apple in a tray makes the full tray bad. So this is the same principle here. And splitting up the bad cells and the healthy cells could help just shortcutting the full recycling cycle. The problem is that you need much of information to do this efficiently. So we've heard so much about how to use and ride your car properly, how to charge your car properly. So, and you need to know the temperature profiles during charging, for example, to make it last longer. So this is the first question mark at the use case level. The user would perhaps want to know how to best make use of his device. Then the collectors need to know their chemistries, the sorting. They need to know the risk they are undertaking, even if in transporting old and retired batteries. So the sorting requires the chemistry and the opening and dismantling. They need the dimensions of the packs, for example, for automation processes. And the separating, of course, they need information about the chemicals, binders, and whatever. So this information is at the recycler side needed. It is available at the suppliers, the miners, the refiners, the cell manufacturers. But this, of course, is their intellectual property, their business case. So they not necessarily like to share that. And in fact, they are located somewhere totally different on the globe. So a knowledge transfer from one partner in this whole cycle to the other is currently not easy. And therefore, the idea came up to facilitate this transfer of information by requiring a digital battery passport, which would allow to connect all the players in the field, the ones who have to provide the information, the ones who would need the information, and for the benefit of the entire economy and system. the European Union has not only imposed this burden on the industry, but also supports with funding projects. So many projects in advance have been funded, which now could help alleviate or facilitate the development of such a digital battery passport. So I'm here as one of the participants in the BASE project, which is short for the Battery Passport for Resilient Supply Chain and Implementation of Circular Economy. So, and we are a consortium of partners who try to set up and build a digital passport that turns out useful for industry. So we have 19 partners throughout of Europe and in fact South America and Africa as well for the suppliers, the miners. We are now 9 months into the project, so we are still quite early, but gaining momentum. We have a funding of almost 9 million euros estimated project costs, and we are very happy to have 4 use case partners from industry to make sure that their input and their requirements are actually met and can be considered during the development of the system. Oh, sorry. So those use cases include e-bus platform from Mercedes-Benz, typical electric vehicle platform for Ford Motors, and marine tugboats, which are really, really large, and stationary applications. So we cover quite a lot of application cases and hope that we can learn enough to make it useful for other users as well. The passport itself has to satisfy several demands. One is obviously access to the passport, so that's would happen via the portal, where the user can register, can identify, and will receive, based on his role in the supply chain, several access rights. So not everybody can see the full set of data, but depending on their role, the recyclers may learn more from the digital battery passport than, say, somebody who would like to buy a car. The portal operates obviously on a data spaces, the infrastructure where the information is connected from the diverse sources. We several passports are currently being under development, and we hope to provide one that comes with certain extras, so with some services that would allow a precise state of health analysis, some remaining useful life estimates that could make the battery itself more transparent, perhaps buyer decisions more informed, such that currently the battery, which is coming as a black box, which carries just price tag, would be then something you could, what do we have to do? Would come with additional information, whether it was sourced in a responsible way, whether it is easily recyclable or not. And so this could even help drive design decisions to more user-friendly battery management systems, more recycling-friendly battery management systems, larger cells, different binder types, whatever. So we have, as I said, tools, methods, and services, and it's quite a huge undertaking in terms of software projects. What I would like to talk about, or what maybe builds the bridge to the talks this morning, is how we represent the data of the physical layer, which is the thing itself in all its stages. So our intention is to capture the physical layer by semantic modeling. Nowadays, all the rage is about artificial intelligence, which is very powerful. But in this case, we would like to resort to good old semantic modeling, open semantic concepts, lay down rules in a very transparent and readable or understandable manner. It is 3-word sentences, actually, of textbook, more or less. So each battery has components. The components are electrodes, separators, whatever. It's not exciting text to read, but it is understandable in contrast to large artificial models, which are black boxes and remain black boxes for quite a while. Everybody has their data. So we have heard from Daniel, they can measure the battery management system, and the data hopefully are available at some point. We want to read for the battery management, for the digital battery passport. We want to get that data to have a real-time estimate how much damage the user has done to his car or not. And those data come in formats. This is the raw data level. So everybody here probably has some data. And they know their data. They're experts of their data. They live in their local environment and they know their data. Those data are typically numbers. And those numbers make only sense if you have your background theory in your mind, the textbook knowledge. So you know about your battery and you know what a voltage means, or a nominal voltage, and whatever, which unit it would carry. This is what we have in our mind, but which is what we have to tell the computer. And here those simple sentences come into play. We are defining those triples, semantic triples, subject, predicate, object, and link them to unique resource identifiers. Those are standardized, machine readable, and this is the mapping between our knowledge, our understanding, how we explicitly define it, and the representation of the computer. The missing link to combine the world of real data and the theoretical knowledge is the metadata annotation, the context. So we have at one point, and this is what everybody who is dealing with their own data has to do, is to annotate the context. So my number coming under the label of voltage with an uppercase letter means cell voltage according to our standardized vocabulary. These ontologies and the third part, they come with standardized terms. And we have to come to terms with standardization in this world. So the missing link, the important part, and this is what we're doing in the BASE project, is that we're trying to capture the physics entirely. So we can describe a battery in all its components and how they are assembled in higher aggregates, and keep track of their history during production, of not only the transformation of the material, but also where on this globe the manufacturers are located, such that we can at least estimate the cost of transportation, for example. All of this adds to the carbon footprint of a battery, and all of this has to be considered. So in combination of the empty ontology together with the annotated data, we obtain the so-called knowledge graph. And this is now queryable. Here you can run your SQL questions and extract the knowledge you have just put into. Plus, you can link information together, so you can draw conclusions. You add your data at one side, you add public data on the other, and then you can combine them in a standardized way. So this is the idea of the semantic modeling behind the battery passport. And luckily, the European Commission has funded many projects in that direction to formalize the common knowledge. So let's say the mother of those ontologies is the elementary multi-perspective material ontology, which is very fundamental, very abstract, but it comes with standardized nomenclature, persistent identifiers, and it's publicly available. Several domains of expertise now have added their own subdomains, which are all compatible with the MO. So we have prefabricated knowledge structures, so to say, for electrochemistry, chemical substances, general processes, the battery value chain ontology, characterization methodology, battery testing, and batteries themselves. So this is a good starting point for us to develop the digital battery passport, which still has some more data to track, like, for example, manufacturers currently don't show up in this picture, but this is more or less, you know, the template is available and we just have to follow the pattern. Yeah, just to illustrate, yeah, what we're intending. So every battery currently comes with a data sheet. If you're lucky, you will find in the internet for your battery data with a number printed on it, a data sheet. Those data sheets come with very basic data, everyone with the voltage and the capacity. If you get more, you're lucky. Sometimes you're missing the chemistry. Sometimes they're very, very long and very detailed. Sometimes they're not. But if you happen to know it's perhaps a lithium manganese oxide battery, then you can draw automatically the conclusion from the electrochemistry, from the chemical formula that is already registered, link it to the European Chemicals Agency, and would extract then the hazardous categorization. This is the information you would have to feed into the digital battery passport. Everybody has to. No passport, no sale in 2 years. And you can do it by hand or you can do it in an automated fashion. The BMS, yes, so we heard just the talk. It's so important to know the usage profiles, the current, the temperature, the voltage all together to learn whether the battery has been in a dangerous region or not. And we're currently developing artificial models that can do the state of health analysis based on historical data. So we have years and years, as Daniel said, of recordings and to observe the fading and the aging of a battery and calibrated on those old data, the services will allow to assess the current state of batteries in a very, very accurately. The whole system is a super stepping stone for creating digital twins. So you can link it to the materials project, and you end up with the crystal structures. You just you decide the level at which you would like to create your models if you want to do testing. I just wanted to mention, because we have heard so much about the batteries today, that the concept is very straightforward to model, for example, processes. So you have a process, you define a pre-process, a post-process, and what goes in terms of matter, energy, and information. Information can be the price, can be the carbon footprint, can be whatever. You define some extra parameters like agents and tools or whatever is needed, and you end up with an output, again, energy, matter, and information. You can connect those, you can keep track of material flows, of, whatever. So the benefits in setting, undertaking the effort to do the annotation step would then be that you can create seamless documentation. You can analyze for the bottleneck in the sequence of processes. You can perhaps have a better basis for automating steps, and you can link the knowledge graph or the data from the knowledge graph. You can extract them to create digital twins for each and every step you think is worthwhile. And you can feed back the data from the model into the knowledge graph, perhaps for use as input in other stages. So, and as Daniel said, yeah, more models, less testing. So it's maybe worthwhile to think of your own ecosystem of data and what you have at home or at work, and yeah, to structure the data, to undertake the effort to do that, and to provide the missing link. This is significant effort upfront before you get a reward, and but it would certainly trigger self-reflection. It would, unlock really the potential that is in your data. And we are currently building up much competence in this direction, and we have a background in compute resources, machine learning, data analytics, and semantic modeling that we would love to find partners here to support you and learn your specific needs and your world and environment. And yeah, with that, I would like to thank you and conclude. I'm happy to take questions. Yeah.
In the beginning, you said about the recycling. So did I get it right? So recycling is cheaper than getting raw materials? No.
Yes. So
because I know from plastics it's more expensive. Oh.
The sourcing of the raw material is very, very energy intensive, and the recycling process. So it's, for example, either it is deep mining under circumstances that maybe not ethical, or it is a concentration of brine water, so aqueous solutions that are left to dry out under arid locations where water is really a scarce resource, and the impact on the environment is tremendous. The materials themselves, lithium, cobalt, manganese, they don't age. It is the inner structure of the battery that is aging. Maybe the organic parts separate as solvents, but they come in high concentrations in those little cells. And if you can separate them, if you know this is the manganese fraction that goes here, this is the nickel batteries those go there, then it is quite efficient to do the recycling. I've just read a paper in Nature about India, where they have carbon thermal ways developed to do it 3 times more efficient than the typical hydrothermal or pyrometallic procedures or processes. So I think there is quite a lot of potential in the optimization potential in the reverse supply chain still to tap. It is done. So we have a partner. We have partners in Turkey and in Lithuania. They are doing it, but they rely on specific. So the Lithuanians just do Tesla packs. They do it automatically because dismantling those packs is dangerous for the humans, and the humans are dangerous for the batteries because so small errors may are associated with risks, and risk is it explodes, but then the battery is gone as well. So they try to do it to automate the processes as much as they can, but they're specialized only on this special type of batteries, because you have a whole production machine which has to work with certain physical dimensions. But I think this will, gain momentum. At least that's the intention and the hopes of the legislators. Yes, definitely. Yeah, I think you were first.
How many or what certain kind of use case you try to how you can realize that with that?
Yes.
And what's the goal? I mean, like, is it just a test with your supporters and everyone that you do it that way, or is there a certain point of time where you say, okay, this has to go live for the European Union or whatever?
Yes.
We say this, everybody has probably with the legal direction that they have to use this platform. Is there, what's the connection between the legal conditions of the European Union and this platform?
So we are developing one digital battery passport, and it's mainly the partners in England who are providing the portal and who will be running the service. So they have compute resources, and I forgot to mention that it will rely on battery blockchain technology to make it hopefully secure. And they will offer it as a service for money. And every update will cost a fraction of a cent, but over time, obviously, this will come with some cost for the customer, yes, but well, if the alternative is you cannot sail in the European market, then I suppose it would be acceptable, and it is supposed to be a low cost. I'm sorry. Yes. Yes. Pardon? This is for the user authentication and for the access control, and for, yes, keeping the data untampered and safe. This is more or less, sorry. This is, I think, the second layer, the analytics and the data space. Oh no, and the microservices and modules. It's the fourth layer, sorry. So the microservices and modules, here is the blockchain and the authorization. No, data space implies that the databases may be located at different sites and are linked together via the semantic modeling then. Yeah. Yes.
You need to trust the source.
Yes, we are aware of that, but unfortunately, I cannot really comment on the technical details here. We're using Catena-X, so we're doing the semantic modeling based on the MO, but it will have a connection to the Catena-X and their standards. One, was heißt das eine? Okay. So I will be available later, and we have a booth in Hall 4, 117. Thank you.